Okay, so section 4.3 is the Hindu-Arabic system, which is our system. The first thing that we're going to take a look at is what we mean by expanded form. Now, we've been doing expanded form in other people's base systems. We're just going to look at an our base system as well. So expanded form means representing 942 as 9 times 100, 4 times 10, and 2 times 1. And you can also represent it, the last step of doing this would be to represent this as 9 times 10 squared, 4 times 10 to the 1. And any idea how I might write 1 as a power of 10? It's a 0. You might remember when you learned exponents that powers of 0 give you a value of 1. So 10 to the 0 would be the number 1. So this is expanded form. That's the final result. Like if you were asked to do expanded form, that's the answer, is the last one there, okay? You can, but don't have to write the one before it. It's just a little bit more intuitive to kind of see it if you want to. All right, so we're going to write expanded form for the number 12,398. And we'll do both steps just so you can see them playing in together. But again, if you want to be able to skip step 1 and write on step 2, that's fine. So we start out with, we're doing single digits. The number 1, what place value is the number 1 in? What does that number 1 mean in this problem? It doesn't mean 1, right? It means 10,000, right? So this is 1 10,000, or 1 times 10,000. What number is 2 being understood as? 2,000, so 2 times 1,000. How about the number 3? 3 times 100. The number 9? 9 times 10. And the number 8? Yeah, 8 times 1. Is that okay? Okay, that's not your final answer. Your final answer has to do with powers of 10. So we're going to write the numbers that are in parentheses as powers of 10. And the real quick and dirty way of doing that is count how many zeros are in the number. So the number 10,000 has how many zeros? 4. So this is 10 to the 4th. The number 1,000 has how many zeros? 3. So this is 10 cubed. The 100 becomes 10 to the 2nd. What will the number 10 be written as? 10 to a power. We've got to have a power to the 1st. There you go. 10 to the 1st. And then the number 1, which we talked about a minute ago, is 10 to the 0. So this is expanded form. And just like we turned something into expanded form, we're also going to turn it back into our standard form. Both of them are expanded form. This is the final answer that your book and that I'm pretty sure my math lab and that I would be expecting to see. So the question of whether or not you have to write the step before it, the answer is no. You could just jump to this step, but this step is necessary to show.
This is the definition difference between the two, just powers?
You're writing it with the powers of the base you're in. This is expanded form in base 10, so we see powers of 10. Yeah. Okay, can I do the next slide? You all right? So on this one, you see a number written out in powers of 10. Okay? And as long as all the powers of 10 are represented, which they are, right? We have 10 to the 5th, 10 to the 4th, 10 to the 3rd, 10 squared, 10 to the 1, 10 to the 0. Right? They're all there. We're not missing anything. Then really all this means is we're going to write down the digits that are multiplied by the powers of 10. So I have a 5 and then what? 0, 3, 5, 6, 8. So this is 503,568. Any questions on that? Pretty easy? Not too bad? Okay. This seems like an odd placement for this, but you'll see why we need it in a minute. I'll show you. This is the distributive property. The distributive property says, and you're used to seeing the distributive property, let me say first, written the other way around. You're used to starting on the right-hand side over here where you've got a parentheses item with addition or subtraction maybe, and something multiplied on the outside, and you're used to seeing this, and you kind of draw arrows to distribute things through. That's usually how this is sort of drawn, right? So that result then is that you end up multiplying the A times the B, the A times the C, and adding those two products. So this is actually just showing you the equation flipped around the other way. It's the same thing. The reason it's done like this is because it's going to be more helpful for what we do when we're doing the adding and subtracting problems, and we see here in a minute. Okay? Are you ready to take a look? Now, the directions say add or subtract in expanded form. So the first thing we have to do is to get things into expanded form, right? So we're going to write down 75 in expanded form. So 75 in expanded form looks like what? Close. 10 to the first. Good. Plus
5
times 10 to the 0. And then we have the same thing with the 3 and the 4, right? 3 times 10 to the 1 plus 4 times 10 to the 0. Okay, just moving it up a little bit. Okay, so in doing this, we can add values that have the same power. So the very fact that I'm allowed to take 5 times 10 to the 0 and 4 times 10 to the 0 and actually add the 5 and the 4 is doing the distributive property. Because you see what we have right now, when we have 5 times 10 to the 0, is we have something like this B times A. And we have the 4 times 10 to the 0, well that's C times A. And what we really want to do is we want to add the A and the B together, or at least, no, they're calling B and C. The B and the C together and leave this part as the multiplication at the end. So it looks a little bit hidden, but it's the distributive property that's allowing us to do this, sort of to group like terms. They're like terms because they're both multiplied by 10 to the 0. But for instance, I couldn't add the 7 and the 4 together because they're not multiplied by the same power of 10. Is everybody tracking with me on that? So it's hidden in the fact that you're doing it, but you use the distributive property every time you add. All right, so what is 5 times 4? I didn't mean times. Thank you, Alexis. That's 5 plus 4. There we go, 9. And then what is 7 plus 3? That's 10. So this is what we get literally if we add. Do you think we get to leave it like that in expanded form? No, that's one of those rhetorical questions, right? What's wrong with it? Say again? It's not our number. What do you mean? We will have to put it together, but we're not even to the point where we can put it together actually yet. So we're one step before that. Does anybody know what the problem is right here, right now?
Well, it's a 10 to the 10.
Yeah, I have a 10 times the 10, don't I? What's 10 times 10? That's 100. Agreed? That's another power of 10. So if I were to take, like imagine that you had 10 $10 bills in your wallet. Okay, is there an easier or a simpler way to have a bill in your wallet besides 10 $10 bills? Yeah, 100. If you're like me, you might change it into 100 just so you don't spend it as easily. So we can take this 10 times 10, and that's actually 1 times 10 to the what? Second, because we've got 10 to the 1 times 10 to the 1, that's 10 squared. How many 10s would we have left over if we took 10 10s and turned them into 100? 0. There's no more 10s left, right? I took them all to turn into the 100. So this would be 0 times 10 to the first. And then I still have the 9 times 10 to the 0 left. So this is the expanded form. It's kind of like when you do something like, scientific notation or whatever. There's a certain form that the answer has to be in at the end. The form that this answer has to be in at the end is expanded form. This line before here was not completely expanded form yet because I still had 10 as in a 2-digit number times 10. Now we're going to do what Alexis said is we can write down what answer that would be, what number that would be if we actually condensed it. What number would this be if we condensed it? 109. And can you add 75 and 34 to double check that that's really 109? Yes. Please understand, this said add or subtract how. What were the directions? In expanded form, which means you can't just take 75 plus 34, figure out it's 109, and write 109 down in expanded form. The directions say you're supposed to add and subtract in that form, and then you can change your answer back. Kind of like what we did with the Egyptians. We add or subtracted in Egyptian, and then we turned it back into our number. All right, let's do a subtraction one so you can see how that one works. All right, so we have to do what first? Turn it into expanded form. So what is 74 in expanded form? 70? How about 7? Maybe I misheard you. 7?
Yeah, 7.
Okay.
And 10 to the
First. Good. Plus what?
4, 10 to the 0.
Okay, so you're imagining you have 7 $10 bills in your wallet, and you've got 4 ones. Everybody picturing that with me? $74 in your pocket, 7 tens, 4 ones. And you are headed home, and last time you were at home, you borrowed $48 from your parents, so you have to pay them back. Specifically, you have to pay them back with 4 tens and 8 ones. And that's the picture you can have in your mind for a concrete example of this. So we have 4 tens, so 4 times 10 to the 1, and 8 times 10 to the 0. Now, this is subtraction, right? And you're subtracting everything, which means you're also subtracting that 8. So it's like you're distributing a negative through. You're going to take away, ones from the ones and tens from the tens, and so forth. But there's a problem. What's the problem?
The 4 is on top of the 8, and some 1 is on the 8.
Right, so if I only have 4 ones in my wallet and I have to give somebody 8 ones, I don't have enough of that particular kind of bill to give them, correct? So what would you do if you owed somebody 8 ones and you didn't have 8 ones? I mean, really, what would you do? I mean, you've got the money, you just don't have the right bills. What would you do? You'd have to break a 10, right? So you go down the hall to some other person and you ask them, do you have 10 ones? And I know in our system, right, we would have 5s and 1s and we might break it differently. But one option would be that they could give you 10 ones and that would work, right? Okay, so that's what we're going to do. We're going to go down the hall and we're going to take one of our 10s with us. So we had 7 10s. How many do we have now? 6. And we go down the hall and we give that person the $10 because they're going to give us back 10 $1 bills. I already had 4 $1 bills, so when they give me 10 $1 bills, how many $1 bills will I have? 14. That's really what borrowing is for us. Borrowing is really breaking apart a place value that's bigger, breaking a 10. That's what it is, it's breaking a 10. And now we can subtract, right? What's 14 minus 8? 6. So this is 6 times 10 to the 0. And what's 6 minus 4? 2. So this is 2 times 10 to the 1. It's addition. Why? Why do I put a plus sign now between these?
Because those two numbers are going to go together, right, to get your ending value.
That's part of it. Yes, I'm going to combine these two back together to get my ending value, and those are represented with addition. Looking above it, why would it necessarily be that it is a plus sign between them?
Oh, because, well, you started out with a bigger positive number.
Right.
Yeah, okay.
Yeah, I mean, and this is kind of why we did it, right? We had a bigger number 14 on top of the smaller number 8, so that we get 14 minus 8, we get a positive number left, so positive 6. So what number is this? How much money do I have in my wallet? 26. And this is the expanded form version. Any questions so far? Alrighty. The next thing we're going to look at is another historical feature. It's, you could probably say it's the first calculator. It's called an abacus. Has everybody ever heard of an abacus before? I'm going to draw you a picture, sort of one in a minute, but it's one of the oldest methods for speed calculating. It's got beads on it. I'm going to draw you a picture so you can see how the beads are. Beads and rods, basically. You've got a middle rod where there's some beads above the middle, there's some beads below the middle. And then the rods actually represent the powers of 10, which means we can relate them straight into our base 10 system. And that's what it's for, is to be able to work with our base system. And on the next slide, I've got a picture so you can see actually what they look like. Okay, did everybody get done writing? Okay. All right, so here's your picture, and we're going to identify the number on the abacus. So write this down first before I start talking about what these things mean. Okay, jot down the picture first. Make sure you fill in all those beads in all the spots where the beads are currently are. Okay, so let's talk about some of the features you're seeing. First of all, on the top, the very top, the very bottom, and the very right-hand side, you want to imagine those are pieces of wood, okay? Everything else, vertical and horizontal, you see those are bars. They're bars that let the beads slide along them, okay? So, again, you want to put the abacus down flat, so imagine it being flat like it is on your paper, because otherwise the beads would slide with gravity, right? That would be unhelpful completely. All right, so a bead is active if it is pushed toward the middle bar. It's inactive if it's pushed away. Now, this is a physical object, which means you can't remove beads unless you break the thing, and that's not the goal. The goal is to keep it all in one piece, okay? So the beads are always going to be there. Above the center rod, you see one bead on each rod. Below the center rod, you see 4 beads on each rod. Everybody good so far? Okay? The beads below are worth the value 1. The beads above are worth the value 5. So if the beads are pushed toward the middle, that's part of the number you're counting. And if the beads are pushed away, it isn't. And we can read the number from left to right or right to left. It really doesn't matter. We're going to read each individual rod. So on this first rod, you notice there's nothing pushed toward the middle. So what number is that? That's 0. And the abacus that you keep drawing are going to always have 5 rods. Okay? They're going to be 5. How about the second one? What number is that? Also 0. On the third rod, however, what do you see happen? 2. There are 2 pushed up here that are each worth 1, so this is actually the number 2. On the fourth rod, What number do I have?
0.
I have 0 from the bottom, but I have the bead from the top that's been moved down, and how much is it worth? 5. So this is the number 5. And then on the last rod, I have what number? 6. 1 bead on top, 1 bead on bottom. So this is the number 6. So this is the number 256. Make sense? Okay, it's a very visual. It's a really nice actual picture of what's going on. So we're going to actually draw our own with the number 70,163. So we're going to draw ourselves an abacus. You're going to draw 5 rods. And then we're going to draw some beads. Oh, I need one more rod in the middle. All right, the number 70, how do I get that?
1, the one on the top is down, pushed in.
Good.
And then 2 from the bottom are pushed up.
Right?
And then the other 2.
There's some really fat beads or something, but go ahead. Yes, and then the other 2 are on the bottom. My beads on the last slide, they looked much nicer. That's 70, okay? I've got to represent 4 beads below the line, 1 bead above the line. I've done that. The 2 beads that are active below the line are pushed up. The 2 beads that are inactive are pushed down. And the 1 bead above the line is active, so it's pushed down towards the middle rod as well. How do I get the number 0? Yeah, so everything needs to be pushed away from the middle rod, right? So we have 1 bead at the top, and I have 4 beads at the bottom. I know, they don't look like very good beads, but they're okay. You still know what I'm talking about. How do I get the number 1? 1 from the bottom is pushed up, and the one that's at the top is still on the top, right? That is correct. How do I get the number 6? 1 from the top, 1 from the bottom, and then 3 more at the bottom. How do I get the number 3? 3 from the bottom.
And then the other one's left down. And then the one on top is up.
Good. So, 2 words of caution. Don't put any extra beads that aren't there. Okay, we didn't break the machine and put an extra bead on. And don't leave any beads off. We didn't break it and bring beads off. Okay, so they need to all have 5 beads on each rod. 1 above and 4 below the line. Okay, last topic. Are you ready? This is lattice multiplication. And it is a very interesting idea. It does something really nice. I'll show you. Jot down the features of it or the steps to it. You create rows and columns for your digits. You divide each box. Compute each product. And then add along the diagonals from right to left. Okay, so whatever number you're multiplying, and it could be a 2-digit number, a 3-digit number, a 4-digit number, it could be a 1-digit number even, and this would work. You're going to put those numbers along either the top or the right. Okay? So 23, 2, space a little bit, and then a 3, and then 1, 8, 7 are stacked on top of each other. The next thing you're going to do is you're going to create a box. The box is going to have rows and columns. It will have 3 rows in this box because you have 3 rows for the numbers 1, 8, and 7. And it will have 2 columns because you have the numbers 2 and 3. So you break it apart into however many you have. That's why you can use this if it's bigger. Okay? That's step 1. I created the rows and columns. Step 2 is to divide my boxes. So what do I mean by that? Well, the division of the boxes is a diagonal division. Looks like this. And that's why this is called lattice, is because this then looks like a lattice. If you guys ever have any lattices or if you've seen them on your homes or anything, but this is what a lattice would look like, or at least an example of one. That's step 2. Step 3 is to compute each product, and you can really do this from whichever box you want. I'm just going to start at the top left because I kind of like to do things from left to right. So I'm going to start in this top box right here, and what this box is going to be is it's going to be the column 2, row 1. So I'm going to multiply 2 times 1, and I'm going to get 2. And I'm going to put it in the bottom corner of that box, down here. Next box to the right, I've got 3 times 1, which is 3, again, bottom corner of the box. Now we're going to see what happens when we multiply and get a 2-digit number. So we've got this second row right here is 2 times 8, which is 16. The 1 goes in the top corner, the 6 goes in the bottom corner. The next box is 3 times 8, which is going to be 24. 2 in the top, 4 in the bottom. All good so far? Last set, I have 2 times 7, so 14. And we have 3 times 7, and that's 21. Okay, a little higher. All right, so that's step 3, compute each product. Step 4 says add along the diagonals. So let me make it real clear where our diagonals are falling. So this is the one diagonal. This is another diagonal. They cut through all of our boxes, making sort of strips, right? Kind of like we've made strips of fabric or something like that. We start in the bottom right-hand corner, and we add up whatever's there, but it's only one number, and it always is only one number. This time it happens to be the number 1, so this is the number 1 down here. And then we're going to add 4 plus 2 plus 4, which is 10. So I'm going to put down the 0, and I'm going to carry the 1. The 1 gets carried to the next column over. I know it's difficult to see, but it's this orange 1 right here. So this orange 1 plus 3 is 4, thank you. 4 plus 2 is 6. 6 plus 6 is 12, plus 1 is 13. So we're going to write down the 3 along that diagonal, and we're going to carry the 1 from the 13 up to the next diagonal. And then we're going to add 1 plus 2 plus 1 for a total of 4. And the cool thing is that this is your solution right here. 4301. Okay, so now let me pause for just a second and tell you a couple things about this. Number 1, it's just as much work as your standard algorithm. What it does, I mean, like some people think, oh, that's a lot more work. It really isn't. It's just about as much work in just about as much space, really. The thing that it does that the standard algorithm doesn't is it separates the multiplication from the addition. If you think about your standard algorithm, when you multiply in that algorithm, if you multiply and get the result of 35, 7 times 5 is 35, you have to write down the 5, carry the 3, then you multiply and add in the middle of the same problem. Do you guys know what I'm talking about? 7 times 5 is 35, and you multiply the 3 here, and then you do 7 times 2 is 14, plus 3 is 16. 14, 17, whatever. All right. Yeah, so the problem is that you're doing the multiplication and the addition at the same time. The lattice multiplication actually separates those operations. You do all your multiplication first, and then you do all your addition second. So it separates that issue, and that's kind of a nice feature, especially when you're first learning multiplication. All right, so number 7, last one. 912 times 483. So this one we have a 3 by 3, so my grid is going to have a 9, 1, 2 on the top, 4, 8, 3 on the right, and you could switch those and it would work fine too. You're going to make yourself a nice big box that's going to have how many rows? 3. And how many columns? 3. Lovely. And each of my rows and columns get divided by diagonal, right? Or divided along the diagonal. And then we're going to multiply. 9 times 4 is 36. 1 times 4 is 2 times 4 is 8. 9 times 8 is 72. 1 times 8 is 8. 2 times 8, 9 times 3, 1 times 3, and 2 times 3. Cool. And then we split our diagonals apart. Just you don't have to literally do this, but I'm just doing it so you can see them a little bit better on my screen. So these are the diagonals that I'm looking at. Bottom right-hand corner, I have the number 6, right? Okay, you don't add any of these white numbers to it. That's the numbers we multiplied by. They have nothing to do with my addition. Then I have 6 plus 3 in the next diagonal, which is 9. And then I have 8 plus 1 plus 8 plus 7.
24.
It is 24. Good job. We're going to put our 4 down and carry a 2, right? So I have 2 plus 4 plus 2 plus 2, which is 10. Write down a 0, carry a 1. 1 plus 7 plus 6? 14. Write a 4, carry a 1. 1 plus 3 is 4. My solution then is 440496. How could you check to make sure that's right without a back of the book? Multiply the first two numbers together, either by hand using the standard algorithm or with calculator, right? Absolutely. So there's no reason to check a back of the book on any of this stuff because it's not going to show you a solution. It's not going to show you the lattice anyway, and you can do the answer with another method. Okay? Have a great spring break, guys.